I'll start the algebra seminar. Today's speaker is Professor Enric Ventura from Universidade Politécnica de Catalunya. He'll talk about endomorphisms of direct products of free surfaces groups and their fixed points. Thanks so much for accepting this invitation.
Thank you. It's 1 hour approximately, right? Good. Okay, so my talk is about endomorphisms and fixed points of endomorphisms in free groups, in surface groups, and then in direct products of them of all kinds. So we play a little bit putting together free and surface groups and see new behavior. Okay, most of what I will talk about is contained in these two papers with my Chinese co-authors, Qiang Zhang and Jianchun Wu. Okay, I will give a little bit of history about free groups, about surface groups. Of course, in here the inertia conjecture, or now better say inertia theorem, because it's completely solved. So this will appear, and I will try to put in context and relate with the other notions. And then in the last part of the talk, I will go to direct products of free and surface groups and see how things degenerate quite quickly. So many new behaviors are possible, even just with small combinations of them. Okay, general notation. G is a finely presented group. This is standard notation for the group of automorphisms or monoid of monomorphisms or endomorphisms. I let morphisms act on the left, so arguments are on the right. I usually do the opposite. So for me, the arguments are always on the left, but my Chinese co-authors were not happy with this, and for these papers, arguments are on the right. Fixed subgroup is what it is, the set of elements fixed by the morphism. And if you talk about fix of a collection of endors, then is the intersection of fixed points. So the points fixed by everybody in the set, even if this set is infinite. If B is finite, then this is a finite intersection, but in all the results, B will be an arbitrary collection, so including infinite intersections. Okay, and then another interesting notion is the notion of equalizer, which is kind of an extension of the fixed subgroup. If you have now two groups, G and H, and you have a collection of morphisms from G to H, then the equalizer of the family is the set of points where everybody in the family act in the same way. So all the points such that beta of X does not depend on beta. Okay, so let's go for 10 minutes. Let's go to free groups. The story began with Dyer Scott in a paper in 1975. There was some other results before this, but this was directly the first paper in this story, saying that if you take a finite group of automorphisms of the free group, Fn denotes the free group of rank n, then the fixed points, the fixed subgroup is a free factor, and in particular has rank bounded by the ambient rank. And they conjectured that for every automorphism, the fix, even if it's infinite order, the rank of the fixed group is going to be bounded by the rank of the ambient. This became known as the Scott conjecture and motivated a lot of research. A few years later, Gersten proved that fixed subgroups are finely generated. His proof was kind of indirect and did not give an explicit upper bound for the rank. He proved by the moment that the fix is finely generated. And Simon Thomas, with a very, very short argument, he extended the same thing to fix of arbitrary families. Of course, if the family is finite, then an intersection of finally many finally generated subgroups is finally generated again. But the point is that this family could be infinite. So even an infinite intersection of fixed subgroups has rank still finite. Okay, and then in a paper by John Stallings from more or less the same time, 1983, he published several results and a conjecture that is quite related with all the rest. So you take two free groups and you take two morphisms. Well, the first of them finally generated, and one of the two morphisms being injective. Then the conjecture says that the equalizer is again finally generated. And a natural question is whether the rank of this equalizer is bounded by the rank of the domain or not. Yeah. Why is it related with the previous story? Well, because if one of the two morphisms is bijective, then the equalizer is the same as the fixed subgroup of going by one and coming back from the other morphism. Yeah. But of course, if none of them is bijective, then the equalizer is not anymore a fixed subgroup. So whether this equalizer has rank bounded by the ambient rank, this is a much stronger question than Scott conjecture. Yeah. Okay. Another connection is the following: if you take a sub F to be a subgroup of F prime, and you take iota to be the inclusion map from F to F prime, then the equalizer of the inclusion on phi is just the fixed points, the fixed points of phi. Yeah, so elements in F such that they go to themselves by the homomorphism phi. Yeah. But again, if you take the equalizer of an arbitrary two morphisms, then it could be much more complicated than fix of something. Okay, the question given by Stallings assumes that one of the two is injective. That's a natural assumption, because if you put kernel in both morphisms, it is very easy to cook an example where the equalizer is infinitely generated. It's not finally generated. Now you kill in F2, you kill the first generator and send B to B, or kill the first generator and send B to B inverse. The equalizer of the two morphisms is just the set of words whose total number of B exponent is 0. But this is the normal closure of A, which is well known to be not finally generated. So if you drop the injectivity of one of the two, then it's very easy to answer the question in the negatives. So the interesting thing is when one of the two morphisms is injective. Okay, soon, few years later, Goldstein and Turner solved Stallings' question in the affirmative. When one of the morphisms is injective, then the equalizer is finally generated. But again, with an argument which gives no indication on what could be a natural upper bound. So as far as I know, I think that the question whether the rank of the equalizer is bounded by the ambient rank in general, I think it remains open, and I have no idea how to think about this problem. No? Okay, in the main, I would say that the main step in this study is Bestvina-Handel result. It was a preprint in 1988, but was published several years later in 92, and they solve Scott conjecture in complete generality. You know? Any automorphism, the rank of a fixed subgroup is bounded by the rank of the ambient. And this was a very influential paper because it was a 50 pages paper in the Annals of Mathematics, where they introduced the train track techniques for graphs. After this paper, there has been lots and lots of other papers developing more and more all the technical properties of these train tracks, which are, well, nice ways of representing automorphisms of the free group by graphs or by homotopes of graphs. Okay, but a crucial point in all this paper is that it doesn't work if phi has kernel. If you put kernel into phi, then many of the techniques doesn't work. Okay, so the same result for endomorphisms at that time was not clear, but just 1 year later, after the announcement of Bestvina-Handel, Enric and Turner proved a very short paper. I think it's just 1 or 2 pages, saying that if this is true for automorphisms, then it's also true for endomorphisms. Yeah? So they just make an argument reducing the general case to the automorphism case. Yeah? So the reduction is just an algebraic argument, which is very nice, and I will use it later. And then the key result is the result for automorphisms. This is the hard bit. Okay, and Turner a little bit later proved that if phi is not bijective, then the rank is at most, the rank of the fix is at most n-1. So maximal rank fix morphisms are automatically automorphisms. Okay, then I started started working in my PhD by reading this, trying to read this paper, this preprint by Bestvina-Handel, and after several years, I could generalize the Bestvina-Handel result in the following sense. No? I introduced the notion of inert and compressed subgroups. This was defined by Andre in his talk two weeks ago. In an arbitrary group, take any group, take any subgroup. The subgroup is said to be inert if the rank of the subgroup intersection with whatever you like is less than or equal the rank of the other subgroup. But by rank in general, I mean the minimal number of generators, right? So a subgroup is inert if it kind of behaves like in the abelian context. No? That when you intersect, you get something of smaller dimension, no? in a vector space. So it's kind of in the free group, it's very well known that when you intersect subgroups, the rank tend to grow. A subgroup is inert if it never grows whenever you intersect with whatever you like in the ambient. And a subgroup is compressed. Compressed is a kind of relaxation of the same condition. Subgroup is compressed when the rank is less than or equal the rank of everything containing H. So I don't take subgroups K in general position with respect to H, but subgroups containing H. Okay, what was the motivation for this concept of inertia? Well, the motivation is the following: if the strong Stalin's conjecture, I mean the question whether the equalizer has rank bounded by the rank of the domain. If this strong Stalin's conjecture were to be true, then the following must happen. Take an endomorphism of the free group. Take an arbitrary subgroup K, and look at the two morphisms from K to F, which are the inclusion, the iota, the canonical inclusion from K to Fn, and the restriction, phi goes from Fn to Fn and restricted to K. If the strong Stalin's conjecture is true, then the rank of the equalizer of these two guys must be bounded by the rank of the domain. But the equalizer of an inclusion and a restriction is just the set of fixed points by my endomorphism which belong to K. Yeah. So proving that fix of an endomorphism is inert, So it's this inequality is just a particular case of the strong Stalin's conjecture. Yeah? We know now that this is true by Antolin and Hykin's result, but this is only, I would say, the first step into this Stalin's conjecture that is much more general. I don't know if it's true or not. Okay, so this was the motivation for me to introduce this inertia property, and then the main result in my PhD was that if you take a bunch of injective endomorphisms of the free group, then the fixed subgroup is inert. Right? This collection, I insist, is finite or infinite, an arbitrary collection of injective morphisms. You take the intersection of the fixed subgroups, this is going to be inert. Yeah? And in particular has rank bounded by the ambient rank. Okay, but again at that point the natural question was what happens for endomorphisms. Yeah? Nothing works for endomorphisms in this way because we strongly use train tracks. So the proof of my result is a variation of Bestvina-Handel's argument mixed with pullbacks of graphs to control intersections. No? Okay, so all this machinery doesn't work for endomorphisms. So at that point we stated the inertia conjecture, saying fix of a family of endomorphisms should be inert, but we don't know. Okay, more relations about these concepts. Inert implies compressed, that's immediate from the definition, and compressed implies rank bounded by the ambient rank. This is kind of the Bestvina-Handel inequality. No? Okay, the first step towards the inertia conjecture was Bergman's result in 1999, who proved that for an arbitrary set of endomorphisms, the rank of the fixed subgroup is bounded by n. So it's proving this for arbitrary sets of endomorphisms. The next step, it was in 2004, proved with my co-author Armando Martino, and we proved that fix of an arbitrary set of endos is compressed. It's like going closer to inertia. And finally, it seems that with in the preprint by Andre and Iago, they can solve completely the inertia conjecture. So fix of an arbitrary set of endos of the free group is inert. Okay, few easy properties of these concepts. Inertia is transitive. If A is inert in B and B is inert in C, then A is inert in C. Free factors are inert. This is very easy to see. Cyclic subgroups, of course, are inert. Rank 2 subgroups are inert. This is the Hannah-Neumann inequality when one of the two subgroups has rank 2. Yeah? Then arbitrary intersections of inner subgroups are inert. This is immediate from the definition for finite intersections, and you have to do a standard argument with infinite intersections for when the intersection is infinite. No? And there is an algorithm to decide compression. So you give me a subgroup, and I can decide algorithmically whether the subgroup is compressed or not. However, these two properties are kind of, these two notions seem kind of opposite to each other with respect to these properties. No? Whether intersections of compressed subgroups are compressed, that's not clear. So it's not I don't know if it's true or not. And whether there exists an algorithm to decide inertia, I also have no idea. The idea why this compressed subgroup is not clear if they are close by intersections is that, suppose H1 is compressed. This is about the rank being less than or equal the rank of whatever bigger than H1. if H2 is compressed, bigger subgroups of H2, the rank is bigger than or equal. But to prove that the intersection is compressed, you are in trouble because you have to deal also with subgroups of this shape. If a subgroup is bigger than the intersection, but is not bigger than H1 and not bigger than H2, it seems that for such a subgroup, there is no information in the hypothesis, but you still have to prove the inequality in rank. No? Okay, so these two questions, I have no idea. But on the other hand, it seems plausible that compressed subgroups are inert, which is the converse implication here. We have been trying to construct counterexamples. We have no single example of a compressed subgroup which is not inert. So even if they look kind of very different properties, maybe this implication is true. Yeah? This is what we call the compressed inert conjecture. Okay, so let's leave this here for a moment and let's go to surface groups. This is the general notation. I call S sigma for the surface and S for the group. The orientable, the group or fundamental group of orientable surface of genus G with a standard presentation, and I put an N at the beginning for non-orientable surface, being the connected sum of K projective planes. And S2 is the Klein bottle, the fundamental group of the Klein bottle, and the Euler characteristic is what it is. Euclidean type is when the Euler characteristic is non-negative, and hyperbolic type is when it's negative. And I include here also the free groups. So when you put punctures, if it's rank 1, this will be considered Euclidean type, and if it's rank 2 or more, it will be hyperbolic. The rank is very well known, that is 2G and K and N, of course, the minimal number of generators of these groups. Okay, what is known about fixed points? Zhang, Wang, and Zhang, they proved the equivalent result to Bestvina-Handel for endomorphisms of arbitrary surface groups of negative Euler's hyperbolic surface groups. Then a few years later, they Wu and Zhang, they generalized a little bit. And most importantly, they proved that if you take an arbitrary family of automorphisms, then the fixed subgroup is inert in G. Yeah? So this is like the result in my thesis, in my PhD, but for hyperbolic surfaces. Okay, and the inertia conjecture again. So you can ask what happens about endomorphisms. Huh? The fix of an arbitrary family of endomorphisms of such a surface group is going to be inert or not. Their proof relies on the free case, and for the free case, it was at that time it was not known whether the endomorphism is in the endomorphism case whether the fix is inert or not. Okay, in our joint paper in 2015, we did in the Euclidean type fixed subgroups are inert. This is not really a big result. It's just an exercise because Euclidean type is very small groups. Huh? And in the same paper, we did a first step into the inertia conjecture. For free and surface groups. No? We take a surface group, we take a bunch of endomorphisms, you fix one of them whose image has minimal rank, and then we prove that for every subgroup K, you have the inequality for the inertia inequality. The problem is that this is not for every K, but for every K satisfying some technical condition. Yeah? This technical condition is relevant, so there are examples where there are subgroups K not satisfying this, so this is proving less than inertia, but at that time it was enough to prove that fix of an arbitrary family of endors is compressed. Yeah? Okay, and it was enough also to prove that the first non-orientable surface group, the connected sum of three projective planes, the inertia conjecture is true. Fix of an arbitrary family of endors is inert. Okay, so this was the state of the art until 2 or 3 days ago, and it was preparing 2 or 3 days ago preparing this talk. I realized that Iago and Andrei's result. He explained 2 weeks ago that in a surface group any retract is inert. I realized 2 days ago that just this result has as a corollary not only what they claim in their preprint, that inertia conjecture is true for free groups, but also for surface groups. An arbitrary surface group and an arbitrary family of endors, the fix of the family is inert. Okay, and let me explain the argument, because this is just recycling an argument from given by Goldstein and Turner long time ago. I recall the definition of retract in an arbitrary group G. A subgroup R is a retract if the identity extends to a homomorphism from G to R. This say projection from G to R is called a retraction, and restricted to R it must be the identity. Okay, so how can we prove that an arbitrary the fixed point of an arbitrary family of endors of an arbitrary surface group is inert? Well, we can assume we are in the hyperbolic case. For Euclidean surfaces, this is an exercise, and take an endomorphism which is not onto, which is not an automorphism. And then let's look at the stable image. So look at the image, which is a strict subgroup because we are assuming it's not an automorphism. And then take the second image, the third image, and so on. This is a descending chain of subgroups, and the stable image is the intersection of all of them. Yeah? This descending sequence, it could be strict forever. There are examples where this never stabilizes. So this could be strict inequalities along all the tower. And then you look at the infinite image. Okay, the rank of the image is bounded by the rank of G, of course, because this is a quotient. And so this subgroup is an infinite index subgroup. If it was finite index, it would be a surface group again of bigger genus or bigger rank. Yeah? So in particular is a free group, and so everything inside here is also free. Okay, but not just the image, but all the images, all the second, third, all the images have rank bounded by the rank of G. So in this descending chain of subgroups, the rank is globally is uniformly bounded by the rank of the initial group G. So by a standard classical result in free groups, the intersection of all these descending tower is a free factor of all but finally many. Yeah, this is a classical result in free groups. You have a descending sequence of subgroups, all of them with rank bounded by a uniform constant. Then the intersection is a free factor of some of them, and then everybody from that point on. Let's say that the D image is the infinite image, or contains the infinite image as a free factor for some big enough D. In particular, this infinite image is finally generated. So it's an infinite intersection, so it could be infinitely generated in general. No, it's finally generated because it's a free factor of finally generated guy. Okay, another another point is that this infinite image is phi invariant. This is just immediate from the construction. You take an element here, take the image, and it's again here. And another observation is that if you restrict your endomorphism to this stable image, then it's onto. Yeah, but these are free groups which are finally generated. So by Hopfianity is an automorphism. Yeah, so the restriction to here is an automorphism. And this stable image, of course, contains the fixed subgroup. If an element is fixed by phi, then you take iterated images and it's equal to the same element. Yep. So the fix of the endomorphism is just the fix of the restriction of phi into the stable image. Yeah? But this fixed point subgroup is inert in the stable image. Why? Because this restriction is bijective. Yeah? Inertia of fixed points is known for bijective for isomorphisms. Yeah? Okay, the point here is that this means that this fixed subgroup intersection with any k has rank less than or equal the rank of k, but for any k contained in the stable image. We don't control what happens when you intersect with k's going outside of the stable image. Okay, but then the key point is that this stable image is a retract of G. And retraction is this very nice morphism. Go these steps ahead by your endomorphism. Then this you land here. This has the infinite image as a free factor. Project to this free factor, and then go back these steps. Go ahead. So apply phi to the minus d. This makes sense, well, because this infinite image, this stable image is invariant, and also because the restriction here is an automorphism. You cannot apply phi to the minus 1 in general because phi was an endomorphism, but you can invert the restriction onto the stable image. Right? And of course, when you restrict this map to elements of the stable image, you go the steps ahead, then you land in the stable image, so the projection is the same thing, and then you go these steps ahead, these steps back, so you end up at the same place where you started. Yeah? So this is clearly a retraction, proving that the stable image is a retract. And then by Andre and Iago's result, the stable image is inert in G. Yeah? But the fixed subgroup was inert in the stable image, so by transitivity, the fixed subgroup is inert in G. Yeah? And all this is about a single endomorphism, but if you take an arbitrary set, then you use that inertia is closed under intersections, and you get that the fix of an arbitrary set of endors is inert. Okay, so inertia conjecture seems that it's completely solved, both for free and for surface groups. Okay, and in the last 20 minutes or so, let me talk about direct products. So let's play a little bit mixing free and surface groups by using direct products. So the point is that the automorphisms are relatively easy to control, and you can still say something. No? A product group. I didn't know what notation should be the appropriate. I call a product group. A product group is a group of the form direct product of finally many blocks, each one being either free or surface or non-orientable surface, with possible repetitions. So G1 could be equal to G2 or G3, whatever. Yeah, so sometimes we will need the block notation. So if you reorganize the blocks by isomorphism, then it will be G1 to some power, direct product, Gm to some power, with the GIs pairwise non-isomorphic. Okay, and then such a product group is called hyperbolic type if all the components are hyperbolic, or of Euclidean type if all components are Euclidean, or of mixed type if there is at least one component of each type. Okay, I admit whatever number of components, but finally many, yeah, of course, and n is finite. Okay, elementary things. The rank of the direct product of two groups is less than or equal the sum of ranks. It's very well known that it could be less. No? Z modulo 2 cross Z modulo 3 is Z modulo 6, which is cyclic again, so 1 is less than 2. But if you play with this surface and free groups, looking at the Booleanization, it's not difficult to see that the rank of the direct product is exactly equal, not less, exactly equal to the sum of ranks. And it's also very elementary to see that such a group has trivial center if and only if it's of hyperbolic type. The center of a group like this is the direct product of centers, and if the surface is hyperbolic, the group has trivial center, and the other way, if it's not hyperbolic, the center is not trivial. Okay, well, let me skip this. Let me another detail. Let me skip this centralizer part. Canceling factors from a direct product is not true in general. There are groups there are groups A and B which are not isomorphic, such that when you cross with Z, for example, they become isomorphic. But again, this pathological behavior does not happen in our free or surface groups. If a product group is isomorphic to another one, even only if the number of pieces, the number of blocks is the same, and GI is isomorphic to HI up to rho 3. Of course, this is only true in the hyperbolic case. Yeah? In the Euclidean case, the torus is the direct product of two free groups of rank 1. Yeah? Okay, our first result. So take a group like this, and let's investigate when Bestvina-Handel's inequality is true. So take an arbitrary automorphism, look at the fixed subgroups, and check whether it's true or not that the rank of the fixed subgroup is bounded by the rank of the ambient. Yeah? Or check whether it's true that the fixed subgroup is compressed. Or check when is it true or when is it not true that the fixed subgroup is inert. Yeah? The results, we have characterization of in all the cases except one. The first result in our paper in 2015 with the Chinese colleagues is the following: take such a product group, then every automorphism has a fixed subgroup satisfying Bestvina-Handel kind of inequality. The rank of the fixed is less than or equal to the rank of the ambient, even only if our group G is either Euclidean or hyperbolic. So even only if everybody, all the components are Euclidean or all the components are hyperbolic. Yeah? When all the components are Euclidean, I think it was this. When all the components are Euclidean, you have several Klein bottles, several infinite cyclic components, and several Z modulo 2s for the projective plane. In this group, it's an exercise to see that every subgroup has rank bounded by the rank of the ambient. Yeah? And so the rank of the fixed subgroup, of course, is bounded by the rank of the ambient, because this is a general fact satisfied by any subgroup. So proving proving that when everybody is Euclidean, the inequality holds. That's just an exercise. The second step in the proof is proving that in the hyperbolic case, it's also true. So if you take a bunch of hyperbolic surfaces or free group of rank bigger than or equal to, and you take the direct product, take an arbitrary automorphism, the fixed subgroup is going to have rank bounded by the rank of the ambient. And then the third step is showing that when you have mixed type, when you have at least one hyperbolic and one Euclidean surface in the product, then there exists a bad automorphism. There exists an automorphism whose fixed subgroup has rank strictly bigger than the rank of the ambient. Yeah? Okay. And the key, more or less the key point of all of this is that what allowed us to prove this kind of results is that it's possible to understand how all automorphisms look like. Take a product group written in the block notation. So I assume the GI is non-pairwise isomorphic, and then automorphisms here are every proposition. Every automorphism looks like something like this. So what are the obvious automorphisms of such a structure? You can take an automorphism of G1, so going from G1 to G1, put together with another automorphism from the second copy of G1 to the second copy of G1, so on, and then compose with permutations of the blocks. If there are 10 copies of G1, I can send elements from the first copy to elements to the second or to a third. So if you take the direct product of an isomorphism, an automorphism of each one of the coordinates, and then compose with a permutation not mixing isomorphism types. This is sigma 1 is a permutation of these n1 guys. Sigma 2 is an arbitrary permutation of the n2 blocks following here, and then this of course is an automorphism of G. Well, the point is that every automorphism of G, it looks like this. Okay, this is in the hyperbolic type. In the Euclidean type, things are more complicated because centers allow much more flexibility. Okay, so when we realize this, then it's relatively easy to reduce the analysis of the automorphisms to the automorphisms of component by component. Okay, let me skip some of the technical proofs, and I will go to the. So let me skip the proof. So using this result, how all automorphisms look like, then we can prove that in the hyperbolic situation, all the fixed subgroups have rank bounded by the ambient rank. Yeah? Okay, and let's go to this, at least showing one of these ugly examples. Suppose we are in the mix situation. So we have one block which is Euclidean and one block which is hyperbolic. Yeah? We have several components, but at least one of each type. Then I want to produce an automorphism whose fixed subgroup has rank strictly bigger. Yeah? We can reduce ourselves to just G1 cross G2, because if there are more components, you can put the identity on all of them. G1 is Euclidean, so take a non-trivial element in the center, and G2 is hyperbolic, so the center is trivial. Okay, and now let's discuss, since the element in the center of the Euclidean part. The center of the Euclidean part is either Z or Z squared or Z modulo 2, or center of the claim bottle, which is Z. So that non-trivial element in the center is just of order 2 for the projective plane, or of infinite order. There is an element whose square is trivial or of infinite order. Okay, and let's distinguish the three cases for the hyperbolic part. If the hyperbolic part is a free group of rank, say, R, then let's look at this automorphism. This is just the automorphism of G mapping, fixing the Euclidean part. So G1 is in G1 is the identity, and in the free group is the identity also. A1 goes to AI goes to AI, except for A1, which goes to T times A1. This is well defined because A commutes with everybody in G1, and TA also commutes with everybody in G1 because T was chosen to be in the center of G1. Okay, now this automorphism maps an arbitrary word on A1 AR to the same word on TA1 A2 AR. If you T commutes with all the A's, so if you move the T's to the left, you get as many as the A1 exponent of W, the total A1 exponent of W. So the fixed subgroup is just everybody from the Euclidean part, and in the free part there are all the words on A1 AR, such that the total A1 exponent is 0 or 0 modulo 2, depending on this T guy being of infinite order or of order 2. This congruent means equal to 0 or congruent to 0 modulo 2. Yeah? But this is G1 times the kernel of this morphism, which is going to the first generator and then reducing modulo the order of T. Yeah? And this is either of rank essentially twice because it's an index 2 subgroup, or of infinite rank because it's a normal subgroup of infinite index. Yeah, so in both cases, the rank of the kernel is strictly bigger than the rank of G2. So this fixed subgroup has the rank of G1 plus this, which is strictly bigger. Yeah? So just playing with a non-trivial element in the center of one of the blocks, you can cook examples like this. No? If instead of the free group you are in the surface group, you kind of do the same, essentially the same argument. Yeah? You have to argue a little bit more, but it's essentially the same. And if you are in the non-orientable case, then you have to put TA and T inverse A to the second generator, because without the T inverse, the morphism is not well defined. It's not well defined because T becomes square here and it gives problems. If you put a T inverse, and it's essentially the same example. Okay, so the analog of Bestvina-Handel is true if and only if you are not of mixed type. Okay, what about compression? For compression in the Euclidean type, we could characterize. Yeah? Take a product group of Euclidean type, and the following are equivalent. Fix of an arbitrary endo is compressed, or fix of an arbitrary auto is compressed, or my group G has one of the following forms: several C's and several Z modulo 2's and no plain bottles, or just one plain bottle and several Z modulo 2's, or several plain bottles and several Z's but no Z modulo 2. Yeah? This is just a case-by-case analysis, and you could prove that in all these cases fixed points are compressed, and in the remaining cases there is always an ugly automorphism whose fixed subgroup is not compressed. Yeah? Unfortunately, in the hyperbolic situation, we could not close an if and only if. We think we are close, but we could not finish the characterization, and we can prove only one implication. If you have a product group of hyperbolic types, so everybody hyperbolic, then if the fixed subgroup is compressed for every automorphism, then G must be of one of these types. But we could not prove that in all these types all fixed subgroups are compressed. The types are just one free group or one orientable surface or one non-orientable of with k bigger than or equal 3 times several NS3s. NS3 is kind of a little bit special because it's small enough to have some special behavior. Okay, and finally about inertia, playing again with Andres and Iago's result about the inertia conjecture, we can complete. So in the paper with the Chinese co-authors, this was also an implication with not an even leaf, but I can recycle into an even leaf using their result. For an arbitrary product group, then the following are equivalent. Fix is inert for every endo, or fix is inert for every auto, or G has one of the following forms. Euclidean 1 or Euclidean 2 from the previous situation. Euclidean 4 is not included there. The numeration is like this because in the paper there was an Euclidean 3 case that now was eliminated by later we eliminated by another argument. So everybody is inert, if and only if you are in one of these two situations, or in the hyperbolic case you have a single component, just one free group or one surface group or one non-orientable surface. So n equals 1, only one block. As soon as you have two blocks, you can cook automorphisms whose fixed subgroups are not inert. Okay, and to finish, let me just present an easy example to show that things are much more tricky here. So for product groups, that compressed inert conjecture is false even for fixed subgroups, of automorphisms. So I can cook a subgroup which is compressed and is not inert, and the subgroup is even the fixed point of some automorphism. And this can be done in a group as easy as this one. Take just F2 times cross Z. So one hyperbolic block and one Euclidean block. The free group is generated by A and B, and Z is generated by C. And take the automorphism which fixes A, fixes B, and inverts C. Clearly, the fixed subgroup is just the subgroup generated by A and B. Anything containing C will not be fixed. And this subgroup, of course, is compressed in G because it's rank 2. So everything of rank 2 is automatically compressed because it cannot be contained in the subgroup of rank 1. But if you intersect with this easy-looking subgroup, so take AB, subgroup generated by A and B, and intersect with the subgroup generated by CA and B. What is in the intersection? All the words in A and B, such that the same word on CA and B give the same results. If you take all the C's out, C commutes with everybody, so if you take all the C's out, you collect as many C's as the total A exponent in the word. So in the intersection there are all the words on A and B whose total A exponent is 0. But this is nothing else but the normal closure of B in the free group, which is very well known to be not finally generated. So we have a very easy looking fixed subgroup, which is obviously compressed, but is very, very far from inert because an intersection with another subgroup of rank 2, the intersection is infinitely generated. And so this fixed subgroup is not inert, so the compressed inert conjecture is very, very far from true. It's just playing with a single extra set. Okay, so That's all. Thank you.
Let's thank the speaker, please. Now, somebody have some questions, comments?
I have a
Well, I
question.
have a general question.
Mhm.
Anybody try to investigate this topic for three manifolds?
There are results. I don't know exactly which results, but there are results about three manifold, about fixed points, and there's all these Nielsen index counting fixed points of maps between manifolds, and there are results.
Automorphisms as well? Automorphism, endomorphisms.
I'm not sure. I never worked in three manifolds, but I can check in the literature. But there are results about automorphisms for sure, and endors probably much less results, but maybe there is something. Yeah.
Some other questions?
Question?
Mm-hmm.
In Stalin's conjecture, if you assume that both morphisms are injective, does it help somehow or not?
One of them must be injective.
Yes,
Otherwise,
this is the condition. But if you also assume that the second one is injective,
maybe for the equalizer is finally generated in all cases, but bounding the rank of the equalizer is I don't know. Enric, I think it's or Goldstein Turner. They proved this equalizer is finally generated with a very nice proof that they can construct the Stalin's graph of this equalizer, and then with an indirect argument they prove that the core is finite. So the group is finally generated, but no indication on a possible bound for the rank. No? It's a similar situation with Gersten. Gersten proved that fix of an automorphism of the free group is finally generated, but with no bound on the rank. And then the bound came with Bestvina-Handel with all the train track machinery. You know? So maybe doing train tracks kind of for two maps simultaneously, but for a single map, it's the train track theory is quite complicated. So I can imagine that carrying two maps all the time is much more complicated. But I don't know. I have the impression that it should be true. So the equalizer the rank should be bounded by the rank of the domain, both in free and surface groups. I don't know. Maybe your techniques can say something about this case. Huh?
And have you considered free products instead of products? So free products of surface groups?
No, but it's natural question. Maybe a similar project works. So we did this because we realized that direct products have very easy automorphisms. The automorphisms are essentially coordinate by coordinate plus permutations in the isomorphic coordinate, nothing else. But isomorphisms in free products, they are also understandable. No? So, natural project would be look at free products of surface groups.
I have a question, Professor Ventura. On the last example, is there an example of a mixed product group with the inertia is not valid for arbitrary automorphisms, but the group does have the finite generated intersection property. So
you mean intersection of finally generated is finally generated?
Yes. So is there a product group with this property that does not satisfy the compressed inert conjecture?
This property is not true here. So this group is not wholesome. No? Here is rank 2, even free group, and the intersection is infinitely generated. So every group where you can embed this property will fail. So if one component is hyperbolic, you have a copy of the free group inside, and if another component is Euclidean, you have non-trivial center, so you have a Z inside, so commuting with the other block. So all these mixed products, they are not wholesome. They all contain F2 cross Z.
I see. Okay. Thank you.
Some other questions? If not, let's thank again Professor Ventura.